So in this area we're going to look at finding area bounded by a limicon. And the limicon that we're going to be interested in is the one whose polar equation is radius equals 1 minus 2 times the sine of theta. And we're going to be asked to find the area between the inner and outer loops of the limicon. So what we'll do is take a look at the GeoGebra graph of this limicon so that we can see what we're being asked to find. I think graphing is an important part of being able to visualize things. So when you look at the limicon, if we're talking about area, there are different areas you could be asked to find here. You could be asked to find the area bounded by this inner loop on the limicon. This is a single curve. So we could be asked to find that area bounded by that inner loop. We could be asked to find the area bounded by the outer loop. We could be asked to find the area between the inner and outer loops. And in this particular case, what we're interested in is the area between the inner loop right here and the outer loop of the limicon. So that's what we're being asked to find. And then my suggestion is when we have a polar equation like r equals 1 minus 2 times the sine of theta, which is the polar equation that's graphed here, I usually like to find out where I am when I am in the 0 degree position. So remember, polar equations, this is the radial axis. So if I'm finding where I am located at 0 radians, I'm really finding where am I located when the angle's at 0. And that's kind of a nice start point. So when you plug 0 in here, you get sine of 0 radians is 0. 0 times 2 is 0. 1 minus 0 is 1. So you discover that you have a radius of 1 and an angle of 0 radians. We want to remember that polar coordinates. You put the radius, and then the angle measure that goes with that radius. So this is the point 1, 0. So we can see that starting at 0, we're in this position. I also can see that the poles are going to be, the y-axis is a line of symmetry. And so when I'm located at the poles, finding the radial arms associated with being at the poles is going to be an important part of finding the area between the two curves. And the basic premise here is if I want the area between the two curves, I need to know the inner area. I need to know the inner area. So I'll call that a sub I. And then I need to know the outer area, the area bounded by the outer curve, which happens to include the area of the inner. So I need to know that, and then I need to take the difference between the two. So the key idea here is I need to do area of the outer minus area of the inner will give me the area between the inner and outer loops. So that's the key idea. And then I want to find out when am I located here at the pole or the origin. And to do that, we need to take our radius formula, radius equals 1 minus 2 sine of theta. This is the equation of the limicon in the polar equation. We need to set that equal to 0. So we get 1 minus 2 times the sine of theta. When does that equal 0? And so we do a little manipulating. We see that the sine of theta needs to equal a half, and then we would take the sine inverse of both sides, so we would get theta equals the sine inverse of 1/2, and we actually know that we get infinitely many solutions, so we could always tack on the plus 2 pi k, and this is going to equal the angle that generates a side ratio of 1/2 is the angle pi over 6, so we get pi over 6 plus 2 pi k. It happens repeatedly. But remember, when we take the sine inverse, we get two solutions. We get the angle and we get the angle supplement. So I should also be looking for the angle theta equals pi minus. To get the supplement, we take 180 degrees minus the angle, or pi radians minus the angle. It's going to be pi minus the sine inverse of 1/2, which is just pi over 6. It's going to be pi minus pi over 6, and we could add on the plus 2 pi k if we wanted to. So pi is the same as 6 pi over 6, finding the common denominator. So this is the angle 5 pi over 6. And it repeats itself, plus 2 pi k. So we already ascertained that when we're right here at this point, this is when we're at radius is 1 and the angle is 0 radians. And what's happening when I look at this, pi over 6, if I let k equal 0, I get pi over 6 and 5 pi over 6, and clearly we get to 5 pi over 6 first. And when you look just visually inspecting this, it looks like, hey, that might be a 30-degree angle, or pi over 6, that has us at the origin. You plug in that pi over 6 into the radius formula, we get sine of pi over 6. The sine of pi over 6 is a half. 2 times a half is 1. 1 minus 1 is 0. So we really have the ordered pair. When the radius is 0, the angle is pi over 6. That puts us rotating through from the 0 position to the pi over 6 position, has us locating ourselves at the origin. So we'll get this back up. So at pi over 6, we're starting right here. And you can think about rotating through to pi over 2 or 90 degrees. It looks like that might locate us into this position. So there's two ways I can think about getting the area of this inner loop. I'm going to be back at the origin. I'm at the origin at pi over 6. I'll be back at the origin when k equals 0 on the second equation, or the second solution I got. I'll be back at the origin at 5 pi over 6 radians. In fact, you can see, if we just grab this guy right here, think about pi over 6. Pi is about 3. So 3 over 6 is a half. So if you start at the angle 0 and you rotate through to about a half, see the point here is moving. There's the radial line out to that point. As we get close to a half, or 0.5, when theta is about 0.5, we should be about at the origin, roughly. It'll be a little bit off because pi isn't quite 3. So there's that 0.5. And then 5 pi over 6, that's going to be 5 times 3 is 15. 15 over 6 is going to be about 5 halves. So at about 2.5 radians. So if we keep this going out at 2.5 radians, swing around till we get to about 2.5-ish, we're about back to the origin. And that's because I'm estimating pi is not really 3. So from pi over 6 to 5 pi over 6, you can see that the point sweeps around the entire inner portion of the Limicon. So if we can actually use that to calculate the area of the inner Limicon. So the area of the inner Limicon could be given by the integral from rotate from pi over 6 to 5 pi over 6. We're back at the origin when we get to 5 pi over 6. And then we know it's a half, 1/2 r squared, but r is given by 1 minus 2 times the sine of theta. So the radius squared d theta, that would give us the full area of the inner. But what I want you to notice is that it looks like if we just rotated to pi over 2, so here we're at the pi over 6 angle, it looks like if we just continued past to pi over 2, so pi over 2 is about 3 halves, so if we go up to about a half, 1.5-ish, you can see we're getting in the down position. So in fact, if we plug pi over 2 in for theta, the sine of pi over 2 is 1. 2 times 1 is 2. 1 minus 2 is -1. So what we can see is that we are in this down position right here. This down position as a polar coordinate is radius is -1, angle is pi over 2. So we're rotating through to the pi over 2 position, and then we're reflecting through, then we're reflecting through to this position here. Again, plug pi over 2 in for radians, hey, rotate pi over 2 degrees, and then we see that we're located down in the -1 position. So another way to calculate the area of the inner would be to take the angle from pi over 6 to pi over 2, and then double that integral, because from pi over 6 to pi over 2, we would get half the area of that limicon. So the area of the inner could also be calculated. An alternative approach would be to go from pi over 2, from pi over 6 to pi over 2, but we double it, so we get 2 times a half is 1. Having a hard time, not having a lot of board space. So the area of the inner would be 2 times the 1/2 radius squared sine theta, square it d theta, there's the square of the radius. So we could double the integral, double this little guy here. At pi over 6, we know that we are back to the pole. At that pi over 6 radian mark, we've rotated all the way around back to the pole. And then the question is, hey, how do I rotate to get all the way around? Because that would give me the area of the outer limicon. Or how can I rotate just into this down position and then get half the area of the outer limicon and then double it? So we know that we've swung, when we get to the angle pi over 6, our point has traveled all the way back around to give us a radius of 0 again, and now it's going to travel around the limicon. And the question is, when does this point get back to here? And what we would need to do is just take advantage of the fact that if we let k equal to 1, from pi over we're at the pole at pi over 6, then we're at the pole at 5 pi over 6. To get the next time we're at the pole, we would let k equal 1 and calculate this. So we could go, we could let k equal 1 on the first equation we used, because they're going to alternate. We're going to this one, back to this one, back to this one. So if we just did pi over 6 plus 2 pi k and let k equal 1, we'll see that we'll be back at the pole at 13 pi over 6. So one way to do this, one way to get the area of the outer limicon, would be to say the area of the outer is equal to, we're going to pick up at the 5 pi over 6 that we left off here when we were back at the pole, and we'll rotate all the way around till we're at an angle of 13 pi over 6 that we got from adding 2 pi to this pi over 6 by letting k equal 1. That will swing us all the way back around to the pole, and then it would be 1/2 still r squared d theta, and the radius is not changing on any of these. So this is 2. I guess I didn't leave myself enough room, so you gotta sit there and erase it. And then the little wiper up here clears everything, and I have to be careful not to accidentally clear everything when I'm erasing, which then makes you swear. So r squared d theta. The other thing to do is to be a little bit clever. You realize that at an angle of 5 pi over 6, we let k equal 0. So the first time we're at the pole, it's at pi over 6, or the origin, it's pi over 6. Then we're at the pole again at k equals 0 here at 5 pi over 6. So the other thing that we could recognize is, hey, I'm starting from 0. At 5 pi over 6, I'm at the pole. That's an angle of 5 pi over 6. It looks like we're in the down position. Looks like we're in the down position down here at 3 pi over 2 radians probably. So you could plug 3 pi over 2 in here. The sign of 3 pi over 2 is -1. 2 times -1 is -2, and 1 minus -2 is going to be +3. So if we rotate, so here's just an alternative approach. If we rotate 3 pi over 2 radians, 3 pi over 2 radians and plug 3 pi over 2 into the sine function here, we wind up getting 3. We wind up getting that this location is located at radius is 3, angle is 3 pi over 2. That's in polar coordinates. So this outer area could also be calculated by finding the outer area here and then doubling it by symmetry. So we could alternatively say that the area of the outer Limicon loop is just equal to 2 times the 1/2 times take the angle from 5 pi over 6. This isn't going to change, but only rotate through to 3 pi over 2 radius squared d theta. And this would be 1 minus 2 times the sine of theta. The reason for doing it this way, just my reason for doing it this way, is it sure looks like you could wind up with some cosine functions when you integrate, and the cosine of 3 pi over 2, and up here, hey, the cosine of pi over 2 is equal to 0, and the sine of 3 pi over 2 and the sine of pi over 2 are also easy, 1 and -1. So introducing those angles that have the simplest side ratios, I think, is a nice way to do it. So again, 2 different ways of calculating the area of the inner, 2 different ways of finding the area of the outer. I'm not going to evaluate the integrals. You know how to evaluate those integrals, but the idea is to get the area between the 2 curves, which is what we're after. That's what we need. We need the area of the outer minus the area of the inner to give us the area that is between the 2 curves.